But now, we're engineers. Let's go and figure out how to deal with it, right? How do I fight the curse of dimensionality? And, in something like decision tree learning, something in the basic algorithm is already to some degree fighting the curse of dimensionality, although you can never completely overcome it. In instance-based learning, that is not the case. So in instance-based learning, explicitly fighting the curse of dimensionality can be the difference between success and failure. Okay? So what is the first way in which we can fight the curse of dimensionality? Any ideas?
Reduce the number of dimensions.
Exactly, right? Get rid of some of them. We don't want them. A lot of these dimensions, they might look good, they might look like they're your friend, but they're your enemy, so let's get rid of them. But, we probably don't want to get rid of them at random, right? So how should we get rid of some of the dimensions? Any suggestions?
Probably look for the ones that are best correlated to the classes.
Precisely, right? Remember, the whole game that I'm playing here is trying to predict the class well, right? So I want to retain the features that correlate well with the class and throw away the ones that don't. And how might I measure that correlation?
I'm kind of blanking out.
Okay, let me give you a hint, right? We saw one such method apropos of learning decision trees. Remember when we were selecting, the best attributes to test at a node? What did we use to select the best attributes?
The information gain.
The information gain, right? We can use that here too, right? Why not, right? That's what we want, right? We want the features that carry the most information about the class. Well, measure that using information gain. So there's two main classes. So by the way, this is always known as the problem of feature selection, right? For obvious reasons. And there are two main classes of feature selection methods. And what we're looking at here is the first one. It's often called the filter approach. Because what we do is we send all those features through a filter, and most of them don't make it through the filter. And then we only use with our nearest neighbor algorithm the features that come out the other end. Okay? We select each feature by how informative it is with respect to the class, and this can be done in many ways, but an obvious one is to use the information gain. Okay? The big advantage of this approach is that it's efficient. Right? I test each feature individually, I measure its correlation with the class. This is linear in the size of my data set. Not a problem. Okay? Even for a large data set. What is the big disadvantage of the filter approach? Again, let me give you a hint. It's similar to the big disadvantage of pre-pruning trees over post-pruning.
You're losing something that might be valuable.
Exactly. Let's suppose that I have a concept that's just, the parity of two of its attributes, of two of the attributes in the data, right? What is the problem of selecting features by information gain? Right? Let's suppose actually that I have no noise, I have no relevant dimensions, right? But I don't know that, right? I just have those, and I apply my information gain to each one of them, right? What is the information gain of each of those two features going to be? Zero, right? They don't look like they say anything about the class. The problem with this filter approach is that it's looking at each filter in isolation. That's efficient, but on the other hand, what happens in most of the interesting cases is that features are not informative in isolation. They are only informative when you combine them with other features, and this method can't detect that. Okay? Despite that, it's still very widely used in practice because of its scalability. It's a very easy, very fast thing to do. And, in a lot of domains where what you really have is just a ton of completely relevant attributes, this gets rid of them pretty quickly. So, for example, in a lot of text classification problems, right, I want to classify documents by the words on them. And, there's 500,000 words in the English language, and most of them are probably not useful at all. Just this test of information gain probably gets rid of them quite easily. Okay?
But the parity example, it could be missing something really good that's in there.
Indeed.
Right?
So in a way you want to use this when there's a lot of irrelevant features and you suspect that there isn't something really good that you're missing. Or another way to put this is you want to believe, and this is the case in text classification, that the information that remains after you've thrown all that out is still good enough. And if you think about it, for text classification, this is the case. Because if I want to classify pages by topic, sports, politics, entertainment, technology, etc., if I only retain the 1,000 most informative words, well, if it has the word baseball, it probably is sports. Okay, so for some things this is fine, but for a lot of things it's not, and that's why we have the wrapper method. Excuse me. The wrapper approach, as the name implies, is you wrap the feature selection around the algorithm. Right? I want to throw out only the features that aren't useful even in combination with other features, but how do I know? I don't know that in advance. I will only know that after I run the algorithm. Well, so let's just do that. Let's run the algorithm with the features. Let's run the algorithm with different subsets of features and see how well it does. Right? So obviously this is expensive. Right? This could be very expensive, but it can be much better. Okay? And in fact, with some methods, including notably nearest neighbor, this can be a lot less expensive than it might seem to be at first sight if we are clever about avoiding redundant computations. Right? Don't just be recomputing all your distances from scratch each time, right? I compute my distance using these features, and then when I add a new feature, right, I don't recompute my distance from scratch. I just take the old distance and I add the new component. Right? So that's the general idea, and now there's two main ways to do wrapper type feature selection: forward selection and backward elimination. Can you guess from just the names what these two approaches are going to be like? What might forward selection be like? It's on the next slide, but let's avoid the temptation to look at it for the moment. Right? How would you do forward feature selection?
Add attributes into your group one by one.
Exactly. So I start out with no attributes, right? Nothing. And then I try, using only one of them. Right? This will probably be bad, right? But one of them will probably do better than the others, the single most informative attribute, so now I keep that one. And then what do?
You have to have some measure in some way.
Very good. So what should my measure be? Or, it can be lots of things, but one thing that it can be, right? Remember, we're just wrapping this around the algorithm, right? So we run the algorithm, right? And now let's say, again, think back to decision trees. What would you do, for example, in post-pruning, right? When we were evaluating different versions of a decision tree. How did we do that?
I mean, you could have a statistical test again, whether the data is the same after.
Yep, exactly. So that's one option, right? Another option is to have validation data, right? So I have some data and I look at that data, right? In fact, I can do cross-validation, and again, I can be very clever and even do what's called leave one out cross-validation, where I only leave out one example at a time. But notice that when I take out one example, most of the nearest neighbors don't change. So actually running through this efficiently can actually be done, in reasonable amount of time. Okay, so I try adding each feature. I measure the resulting accuracy. I pick the best feature, and then I try adding, one of the other features, and I keep doing this until when? Right? When should I? Obviously, if I wind up adding all the features, it stops right there, right? But why would I stop earlier than that?
Accuracy doesn't improve enough.
Yeah, or in fact, it could even go down, right? If I come to a point where I now say have 10 features, and I try adding each one of the other 90 features as the next one, and in all cases it makes things worse or not better, then, well, this is where I should stop. Okay? So this is forward selection. What do you think is backward elimination?
Start with all of them, remove one at a time.
Exactly. I start with all of them, and I remove one at a time. And when I remove, if when I remove each one of them, it always makes things worse, well, then I stop right there. What hopefully happens is that many of them are irrelevant, so when I remove them, things don't get worse. Okay? And so, I remove one of those and I keep going. Okay? So, question for you. What are the relative advantages and disadvantages of forward and backward selection? What is an obvious advantage of forward selection over backward selection? Let's suppose that I have 10 relevant features and 1,000 irrelevant ones. Which method do you think will be faster?
Forward.
Yeah, forward selection is going to be way faster, right? This is a lot like pre-pruning and post-pruning, right? Very similar. With post-pruning, I have to grow the whole tree and then prune it back. It's a big waste of time. With forward selection, I just quickly, hopefully, zero in on the relevant features, and the other ones I don't have to deal with. Okay? But now, of course, there's also a big disadvantage of forward selection compared to backward selection. What might that be? Let me give you a hint, right? Go ahead.
I'm sorry, I was saying, is it the same as you were saying about missing, eliminating certain information too early before it?
The hint I was going to give you is a hint that I will, give you many times, and it's just this word parity. Right? What is the problem with forward selection if your concept is parity? It falls flat again, right? It's just like the wrapper method in this case. There are cases where the wrapper method fails and forward selection doesn't, but for this type of problem, it's exactly the same issue, right? I'm doing my forward selection, and I immediately think that none of the features is useful, so I don't add any of them, and I'm hosed. So it was fast, but I got the wrong answer. Okay? And if most of the features are relevant, you actually don't get that big of a performance benefit anyway. Okay? On the other hand, what usually happens in practice is that the vast majority of the features are irrelevant. So there is a big performance advantage of forward over backward. On the other hand, you could miss a lot of things, which is why you want to be aware of both methods. Okay? Questions?
So in terms of instance-based learning, backward elimination would mean, let's say you were in a very high dimensional space and you have 200 points closer.
Mm-hmm.
You pursue all of them?
No, so notice the following, right? We need to distinguish between feature selection and instance selection. Right? We're actually going to talk about instance selection a little bit, but for the moment, we're always assuming that you keep all of your instances. Right? So I have my big table, right? One instance per row, right? What we're talking about here is making the table thinner, not shorter. We're talking about throwing out features. I still have 200 examples.
That are closest to
let's say 200 whatever, right? But the number of examples has not changed. What has happened is that there are 200 examples in a lower dimensional space. Okay? Questions? Okay. So we have here pseudocode for both of these, but I'm not going to go over it here because we already saw what it does. I encourage you to look at it at home. But there's more things that we can do, right? Feature selection is a bit drastic, right? Well, what if there was a little bit of information in that feature? Do I really want to throw it away? Maybe I can somehow squeeze the juice out of it without letting the noise swamp the signal, right? If some features are very informative and some are not very informative, well, I don't necessarily just want to completely throw away the informative features because there could be a lot of them, and when I do that, I could actually be compromising my performance. Okay? So the next method that we're going to look at, and it is a very, very widely used one, is what's called feature weighting. And again, it's a very natural idea, right? What I'm going to do is I'm going to give weights to my features. Again, notice that this is different from giving weights to your instance, and in fact, you could do both, right? What I'm going to do is I'm going to say, oh, if this feature is very informative, it's going to count for a lot, so I'm going to, in my distance measure, right, I'm going to put weights on the contributions from the different features. And the more informative features, according to some criterion, will have a higher weight. Okay? Another way to think about this is that what I'm doing when I'm doing feature weight is I'm flattening the less important features. It's like saying, let's say, like my instance space was this room, and like the coordinates on the floor are very important, but the height is not very important, right? The height, maybe I don't want to throw it away completely, but I want it to count for less. What I'm going to do is I'm going to flatten the room, right? So now the variations in height make a relatively small contribution. Maybe they can break ties between things that are at the same distance horizontally, okay? In the limit, of course, if I flatten things all the way, that dimension disappears. So feature selection is sort of like a limiting case of feature weighting when the weight becomes 0. Okay? But in general, the weights could be, very varied. Okay? So how exactly might I find the weights for the features? Again, there's many ways, but probably the most widely used one is to use continuous optimization. Right? Use gradient descent. Right? I have my measure that I care about, accuracy or some other measure of error. Right? Let's suppose that it's a continuous function of my weights, right? If it's not, I'm going to have to be more careful, right? And then what I'm doing is like think of the value of my error as a function of those weights, right? What I'm going to look for is the value of those weights that gives me the minimum error, okay? And I can do that using gradient descent. We will look in more detail at gradient descent a little bit later when we talk about neural networks. But for the moment, you could just think of it as it's a method for finding, the value of the inputs to a function that make the function as small as possible. And as the name implies, it's kind of like if you want to find the value, just walk downhill, right? Walk downhill with the weights. Start, for example, with all the weights equal. Find the direction of steepest descent and keep following it until you're in the valley, right? And at that point, hopefully, those are your best weights. Okay? And that's feature weighting for you. Okay. I'm mentioning a bunch of these things fairly quickly. Of course, there's many technical details, but I think the important thing is for you to A, be aware of the general class of methods, and then B, the kinds of things that you can use to make them better, right? Such that if you run into a problem where feature weighting is really what you need, then you can sort of look into that in more detail, okay? Okay, so why don't we take a break here, right? So it's 5:20, right? So let's break until 5:30, okay? And then we'll do the rest.